In problem number 6, we have traffic flow defined as the rate at which cars pass through an intersection measured in cars per minute. And the traffic flow at this particular intersection is modeled by the function capital F, defined by capital F as 82 plus 4 sine of t over 2 for t between 0 and 30, where capital F of t is measured in cars per minute, t is measured in minutes. A. To the nearest whole number, how many cars pass through the intersection over the 30-minute period? Well, since capital F of t is a rate, if we take it's the rate at which cars pass through the intersection, the integral of that rate from 0 to 30 will tell us how many cars pass through that intersection during that time interval. And to evaluate that, we're going to go to our calculator, go into y equals, and I have set up there 82 plus 4 sine of x over 2. And if I want to evaluate the integral of that from 0 to 30, go back out to the home screen, to math, scroll up to fn int, vars, y vars, function y1, comma x is the variable of integration from 0 to 30. And that gives me a value of 2,474 rounded to the nearest whole number. And that's the unit of measure would be cars. We'll close the calculator and go on to part B. Is the traffic flow increasing or decreasing at t equals 7? And I state that traffic flow increases when f of t is greater than 0. And I just need to see whether f of 7 is going to be greater than 0 or less than 0. And so I'll bring back the calculator. Since f of t is the function in y1, all I need to do is variables, y variables, function y1 of 7, and that's 80.596. And so since that is positive, and therefore traffic flow is increasing at t equals 6 at 7. Okay, so that is part B. We'll go on to part C. Close down the calculator. Part C says, what is the average value of the traffic flow over the time interval? Since the traffic flow is our function that's defined there, the average value of a function is given by the integral divided by the width of the interval. And this involves the mean value theorem. So the average value of the function traffic flow will be over the time interval from 10 to 15, 1 over 15 minus 10 times the integral from 10 to 15 of f of t dt. And we'll bring back the calculator and we'll find the integral. Math, fn int, vars, y vars, function y1, comma x from 10 to 15, and then we want to divide that whole thing by 5, which is the width of our interval, and that will be 81.899 cars per minute, which is the average value of traffic flow over the time interval. We'll close down the calculator and go on to the final part there. Part D says, what is the average rate of change of the traffic flow on the interval from 10 to 15? So the average rate of change is different from the average value of traffic flow. The average value of traffic flow is the integral divided by the interval. The average rate of change is just the slope of the secant line connecting the beginning and ending points of the interval. And so that's just f of 15 minus f of 10 over 5. We bring back the calculator. We have variables, y variables, function y1 of 15 minus vars, y vars, function y1 of 10, and that gives us 7.587. We're going to divide that by 5 and end up with 1.518. And the units there are cars per minute squared. That means that the traffic flow is increasing at a rate of 1.5 cars, roughly, per minute every minute. And so that brings us to the end of problem number 6.